Hello, we're Group 22, composed of Oscar, Claudia, Lloyd, and myself, Ayaz. Our project is 2D object detection for vehicles on the road. In our contemporary society, image and video object detection is gaining popularity by the day as we gradually transfer human responsibilities into the hands of artificial intelligence. One of the sectors which has seen the biggest change in responsibility is the automotive industry as they begin to manufacture autonomous vehicles. The motivation of our group stems from our collective interest in this next phase of automobiles. And one of the many responsibilities of a functioning autonomous vehicle will be, hopefully, the ability to classify objects that it encounters on the road, especially other cars. Hence, we aim to build an object detection model which is able to detect cars on the road. Thank you.
The top three existing works we'll be looking at are Ayaz's model of SSD, which is from the paper SSD Single Shot Multi-Box Detector. It uses the COCO, Pascal, and VOC datasets. Its accuracy was 76.4%. I will be using the Faster RCNN, which is from the paper Faster RCNN Towards Real-Time Object Detection with Region Proposal Networks. This builds off of the previous CNN and then Fast CNN models. It uses the same data sets of COCO and VOC, and it had an accuracy of 75.9% on the VOC 2012 test set. Cooper will be using the YOLO model from You Only Look Once, which uses the Kitty and VOC datasets. It had the best accuracy of 87.54 on the VOC test set. The datasets these researchers have used are ImageNet, COCO, Microsoft Common Objects in Context, Pascal VOC, Pascal Visual Objects Classes Challenge, and Kitty, the Karlsruhe Institute of Technology and Toyota Institute Vision Benchmark Suite. The reason why they all share these datasets are because they are very popular for autonomous driving. It is not easy to create data, and these are highly regarded sets. They get updated often and have their own competitions frequently. By combining all these datasets to train their models, researchers are able to achieve better accuracy than if they only used a single dataset to train their model. Here for reference is the Faster RCNN results when compared to just COCO versus Fast RCNN and Faster RCNN. We can see the accuracy improves as more data sets are used.
So I worked on SSD. SSD is short for single shot detection. Generally, the output of an SSD model should include a couple things. This is generally also true for other machine learning models. And one is basically the probability value of an object that is inside of the bounding box that the model ends up creating. Second is the height of the bounding box. Third is the width of the bounding box. Fourth thing that's important is the horizontal coordinate of the center point of the bounding box, and the fifth is the vertical coordinate of the center point of the box. SSD models have two components to them. One is called the backbone, and the other is called the SSD head. The backbone is basically a pre-trained image classification network created for feature extraction purposes. The special thing about them is that since we do not want a conclusion for a model before passing it on to the SSD head, we remove the final classification layer. We take it out so that it does not come up with a prediction before we pass it on. And then the SSD head is just one or many convolutional layers added to the end of the backbone algorithm in place of the final classification layer. And this is done basically because of a need to create bounding boxes and classes of objects.
I have chosen the Faster RCNN model. To understand the architecture for this model, we must first discern the differences between its predecessors, RCNN, regional convolutional neural networks, and fast RCNN. The biggest problem each of these iterations faced was how to decide and calculate the regions for the CNN to use. Originally with RCNN, the regions were hard-coded in and had to be of a specific size to be accepted by the model. This was extremely computationally expensive and took plenty of time. This drove researchers to look for solutions to improve the region selection and creation portion of the algorithm, which they eventually built for fast RCNN. The solution was to use selective search, which was an improvement but still computationally expensive. Work was eventually published for RPN, Regional Proposal Network. These could efficiently use a neural network to select and present regions. The importance of this algorithm was huge. Regions could now be calculated in parallel, effectively making the computational cost marginal. This development was coupled with fast RCNN to create the state-of-the-art deep learning object detection model we know as faster RCNN. The single unified network uses convolutional layers to extract regions of the image and map these features to a feature map. The new RPN module calculates possible proposals from the feature map, and the rest of the CNN network uses these proposals and original feature map to calculate regions of interest and to classify the possible objects. The training of these models was done on each combination of the COCO and VOC dataset. This testing was also done on each of these datasets. Since they are the most popular datasets, which this model competes in, comparing all the results allows the researchers to contrast the results to previous models used in past competitions, along with seeing the performance when presenting more data. The results of their findings were illustrated here, where we can see an increase from 39.3 to 42.1 on only COCO training and testing when compared to the old model, fast RCNN. The peak performance of the network occurs when training on the COCO VOC07 and VOC012 training and validation sets, and then testing this model against the Pascal VOC12 test set.
Hi, my name's Cooper. I chose to implement a version of YOLO. YOLO stands for You Only Look Once. So how that works is it performs bounding box prediction and class prediction of bounding box all in one iteration, or it only looks once. I looked specifically at the V3 architecture. As you can see here on this slide, there's a diagram of this architecture. YOLO version 3 uses pre-trained DarkNet 53 as a backbone of the network for feature extraction. This is 53 convolutional layers, and then YOLO version 3, the rest of the architecture is another 53 layers on top of the DarkNet 53 layers. And so that's a total of 106 layers. A little bit more about the backbone. It's different from its predecessor, which was DarkNet 19, because it uses residual connections, and it has obviously the increased number of layers up to 53. So as you can see in the diagram here, there are 3 different sized feature maps which are used for one-to-one mapping, and that's how the model performs feature detection for the classification of objects. So moving on to the next slide here. Moving on to the next slide, we're going to talk about the data sets used and some results from YOLO version 3. So the backbone of the network, the DarkNet, is pre-trained on the ImageNet dataset, and then the Kitty dataset is used for validation and testing, and then the VOC dataset is also used for testing and is also used for a mean average precision calculation, which is shown in just a second. So some results are that YOLO version 3 is relatively lightweight compared to SSD and RCNN. because it allows for faster iteration. YOLO version 3 has lower GPU costs, therefore, so which is better. Because we want to evaluate like performance in real time. This requires like really fast inference time, so this is why I chose to use YOLO version 3 architecture, because it's really fast, and version 4 is quite a bit slower. So the change I'll be making will be to incorporate shallow feature mapping to achieve better results for the detection of smaller objects like humans. As you can see in the graph in the top right here, it doesn't perform as well on the detection of smaller objects, and specifically humans here in this case, but it does perform very well for those larger objects like cars, and the tram and trucks as well. So I'll aim to achieve similar results to YOLO version 5 in its ability to detect these smaller objects, and I'm going to be working off the YOLO version 3 code, which I've shown the results for here. So the results for this on the VOTC test set were a mean average precision of 87.54, so it's fairly accurate and precise. Thank you. Hello, I'm going to conclude up our slide show today by discussing each of the 3 models that we've chose to implement. So to give a quick summary on YOLO and the different versions and papers that we read, we learned about YOLO version 1. You can see in the diagram at the very top left. YOLO version 1 was very fast, but it was fairly bad at classifying smaller objects, and this was a paper by Redmond J. Yes, and it had a 57.9 mean average precision. So moving on to YOLO version 3. YOLO version 3 was more accurate, but it still had like a bad time classifying humans. And this is the model I'm going to be working off of and trying to improve its classification of smaller objects, and at classifying humans specifically. The model that I looked at, some were able to achieve 87.54 mean average precision, so fairly accurate overall. Version 4 had additional features that made it more complicated, and really took away from YOLO's simplicity, and this was Buchowski's paper. And this had a 62.8 mean average precision. But yeah, it added too many features which were convoluted, and this was an issue of this paper and the specific version 4 model, was that it took away from the simplicity of YOLO, which is really the essence of what makes YOLO good. So then version 5 was very fast and accurate in all its classifications, including small objects, and so version 5 really improved on the classification of small objects and kept its quickness, and that paper was done by Xiao B. And the mean average precision was 59.6 for that. So then moving on to SSD, quick summary. So the problem addressed was simplified object detection, focused on increasing the speed of detection. The data uses Pascal on the VOC 2007 and 12. So this is called multi-box single shot detector. The results at the time of publishing were 76.4 mean average precision, and some known shortcomings were that they noticed for some objects, such as dogs, which were relatively big in the input images, the performance isn't much different compared to the two-stage method, 88.7 versus 90.4. However, like for other objects such as cars, SSD performs worse than the two-stage method. We think this is because SSD can't handle the small objects, since the input image is too small and it loses the important details of the small objects. So that was a summary of SSD, and then moving on to the final model that we covered is RCNN. So the problems addressed here were computing proposals with the last test time computational bottleneck in state-of-the-art detection systems. Data used COCO, VOC 07, and 12. So the results of mean average precision were 75.9 on VOC 12, which was much faster than previous fast RCNN, which averaged 39.3 mean average position, and the shortcomings discussed in these papers, in the paper Ren S, they didn't discuss very many shortcomings that are worth discussing here. And the previous models use selective search for the region proposal, which is very slow and computationally expensive. And the new model implements RPN to tackle that problem and allows for parallel computing, which greatly increases speed. So that's why we're not using novel RPN or previous RCNN. And so that's a conclusion. That's all three of our different models and the histories of the papers we looked at, some of the shortcomings and the results that we found. We've each discussed how we're going to work towards making changes and bettering these three models to try and accurately classify all the different objects that you could possibly see on the road through using all these different data sets that are widely available to the public and are very large, and there's a lot of work done on them. So that's our group project, and thank you for listening.